started to introduce, right, the concept of chirality. And the way that we explain chirality is that you needed to have a site, a carbon, so we're looking at a carbon, and that carbon actually has to be drawn like so. So the carbon is sp3 hybridized. First of all, carbon is sp3 hybridized. That carbon that is sp3 hybridized needs to have 4 different things around it. So we have 4 different atoms around it. All right, there are 4. There is a man-made way of assigning absolute configuration, and the man-made way of assigning absolute configuration is giving priorities to these atoms based on their atomic number. Okay, the highest the atomic number, the highest the priority. So iodine, that is element number 53, will be priority number 1. Bromine, that is element number 35, will be priority number 2. Chlorine, that is element 17, will be priority number 3. And the hydrogen will be the lowest priority, which is number 4. In order to assign the absolute configuration that is only going to be R or S, you literally have to take the molecule and you have to turn it into what we call dearly in your face. Right, so if your molecule is like this and your hydrogen is at the top, which is the lowest, you physically have to rotate and put it in your face. I think this picture appears many, many times. It appears many, many times, and I want to show you what your book is saying. Right, I want to show you what the book is saying. So the book is telling you that a chiral carbon is one that has 4 different attachments, just like we've been saying. Right, so you have 4 different attachments. They have chosen to label them all already with the priorities, the 1, 2, 3, 4s, everybody, the 1, 2, 3, 4. We can give the little carbon a little asterisk to denote that it is chiral. And then they're saying that these images, right, if you have a compound and you have a mirror, anything will have an image provided you have a mirror. Okay, we'll say this again. So if you have a mirror, anything will have an image. You take that molecule to the mirror sees this image, but what is important is that when you go ahead and you lift that image and you try to superimpose, it does not. Like we did in the lab yesterday, if it does not superimpose, those structures are said to be enantiomers. And enantiomers are isomers. They are stereoisomers, right? And so here's the story. All asymmetric carbon atom is the most common example of a chirality center. Does anybody understand what that means? So any carbon that has all these 4 different things has a chirality center. Oh, there's no way I can follow all that. Whew, I'm already getting killed. All right, so I cannot. All right, so here we go. So what they're trying to say is if I come here and I draw, I put my mirror, so this is my mirror, and you have to draw the mirror image, what you're doing is this. You're drawing the mirror image. Here's the Br, and you have that carbon. There at the very top you have the iodide. Over here you would have the chlorine. And in the back you have the hydrogen. That's what we do with the mirror images, okay? When we're assigning now the absolute configuration and your choices are only R or S, when I'm holding this one from back here, right, when I'm holding this one from back here, if I see the rotation, I'm kind of like connecting the dots. Is everybody? You're kind of like connecting the dots. 2 is after 1, 3 is after 2, and you do that rotation, and that rotation that you're doing this way, wow. You can see where my nerves are today too. That rotation that goes like that is called the R, or the clockwise rotation. So that R is clockwise. The enantiomer has to be the opposite, so its mirror image has to be S. So even without trying, I know that this has to be S. And the S is then called the counterclockwise rotation. Counterclockwise rotation. And we do the same thing, we count. This will be priority number 1, and this is priority number 2, this is number 3, the 4th is in the back, and now you see the rotation. You're connecting the dots, you're like not seeing that one in the back. You're connecting the dots, you go, you go, you go, and that's going counterclockwise, okay? Is everybody there? This is only one chiral carbon. Is everybody, this is just one chiral carbon. And this little asterisk is denoting that that carbon is asymmetric, like your book wants to call it. So they refer to that book, that carbon as asymmetric. They also refer to that carbon as chiral. They refer to that place as a stereocenter. Oh my gosh, all of this means the same. Okay, all those paragraphs that they keep popping in this PowerPoint, they all mean the same. Okay, everybody, that's all means the same. All right, so let's take a look what happens when we start getting these groups to be larger. And I think we were doing that last time when we were together, but we want to make sure that we see what happens when the groups are larger. So I'm coming over here, and we have to find a tool, right? We're finding a tool to deal with these things. So I'm just going to go ahead and put carbons. And this is the beginning of introducing double bonds, okay? I'm going to put a CH3 in the back. And if I put over here a CH2, CH3, I think everybody already knows which one has the highest priority, yes or no?
Yes.
Okay. So I heard something here. Ethyl has the highest. Okay, so I'm hearing that ethyl has the highest by everybody, but why does ethyl have the highest is what I want to know.
Least hydrogens?
Okay.
In place of where the hydrogens, you have a carbon which has a higher atomic number.
There we go. Okay, so it isn't that it has the highest number. What you're looking for the first difference, okay? You're looking for the first difference. This is going to be really important when I'm adding the other ones, all right? So the methyl begins like this. The methyl starts out like that, and like that, right? That's your methyl. Your ethyl has a hydrogen and a hydrogen. So far, those were equal. Okay, so far the methyl and the ethyl are equal. When you go to the next attachment, that's when you see the first difference. That carbon, higher atomic number than the hydrogen, has made the ethyl then be the higher priority. Is everybody okay? All right, I'm going to continue to add later, so you're going to tell me. Whoa. I have photophobia in place. Okay, so I come over here, and I'm going to do this, and I come over here, and I'm going to do this. Okay, and you're going to go ahead and label the priorities of these guys, because now you know all of this. So based on the priorities of these, what's going to happen? Who's priority number 1? How are we going to do this? Okay, so now what you're looking back again at the board, what you're looking here back again on the board, then ethyl had this, that. Now we have this that still looks like so. This that still looks like so, where you have your hydrogen there, right? So we're looking at everything the same. Now that has the O and the H, while the other one has the hydrogen and the Br. So, right? So all of this really, like, did not count, because it's all the same for all of them. right? So all of that did not count, they're all the same. From here on in, when I'm gonna create these gigantic ugly things, you've gotta look for the first difference, the point where you find the initial difference. Right now, we have a hydrogen, we have a carbon, we have an O, and we have a Br. So you've gone past the direct attachment, we have to go one further, okay? And with that story of one further, you can see now, I knew it, you can see now that once again, your bromine has the first priority, the CH2OH has the second, this has the third, and back here has the fourth. You're going that R rotation, you know, it's enantiomer. If I say, what is the enantiomer?
The mirror image.
The
S.
enantiomer is S, okay, which is the mirror image that is not superimposed, okay. Let's take a look at this other molecule. This other molecule looks like this. I'm gonna come over here, and we start introducing double bonds. When I start introducing double bonds, I can draw my picture like that also. Like so. This is gonna be my CH2, CH3. Over here, I'm gonna have a CH3, CH3. Over here, I'm going to have a C, double bond C. And up at the top, I'm gonna have a C. Ay, ay, ay. There we go. All right. So when I look at the molecule, your book makes like such a crazy way of showing what happens over here, right? And I want to try to make sure that I explain this very well. If we're looking between the ethyl and the isopropyl, right, if we're just going to concentrate between the ethyl and the isopropyl, which one would have the higher priority?
Isopropyl.
Okay, is everybody seeing the isopropyl as the higher priority? Yes or no? Everybody, yes? Yes? Okay, if you're looking at the ethyl, you know, like Amber is telling me, you know, one hydrogen and a methyl kind of go away in both of them. Is everybody? One hydrogen, one methyl and a methyl go away, one hydrogen and a methyl go away, and you're left now with a methyl over here. So the isopropyl has the higher priority than the ethyl. Everybody sees it, or I have to explain it any differently than that? Okay, when you're looking at carbon-carbon double bonds, the best way to see a carbon-carbon double bond is like this. So this is like a commercial break, right? Commercial break. I am bonded to you. This carbon is bonded to the carbon that is the stereocenter, right? So this is the stereocenter. And now I'm bonded to a hydrogen, and I'm bonded to a carbon. Can everybody see all that? I stereocenter, I'm gonna do the little star. I stereocenter, I'm bonded to a carbon that is bonded to a hydrogen and to a carbon. And the way that they explain the double bond is break it up, you're bonded to a carbon, and I'm bonded to another carbon. It's like break up, so that carbon that has a double bond directly attached is like it's bonded to two carbons. Is everybody seeing that? Okay, a carbon that is doubly bonded is a carbon that already has one single bond to one carbon, that one. And it's like that bond can be broken, and I have a carbon and you have a carbon. It counts as two carbons. Let me show you, let's see if they have something here so that you guys can see. Look what the book does. Maybe this is better for you. Hold on a second. Maybe this is better for you. Sometimes a slide. So they're telling you when you're starting to have multiple bonds, when you start having multiple bonds, treat them as if you have more than one. So if a double bond to a carbon, everybody over here, if you have a carbon-carbon double bond, you keep one bond, so you're keeping one bond, right? And then treat that double bond like you broke it equally into 2 carbons, so everybody gets a carbon apiece. So it really counts as 2 carbons at that point of attachment, yes? Okay, if you have a carbon triply bonded to a nitrogen, or double bonded to the nitrogen, if your carbon is double bonded to the nitrogen, then you're doing the same thing. You keep the first bond, you're keeping like the first bond, the carbon nitrogen, and then you say, oh, okay, well then it's like I'm bonded to 2 nitrogens. A carbon double bonded to nitrogen is like you are bonded to 2 nitrogens yourself, you know? If you have a triple bond, then take a look at this craziness. If you have a triple bond, then it's saying that you're having one bond is still the original bond, so keep your sigma bond, okay? In the case of the triple bond, keep that sigma bond between your carbon-carbon, the original triple bond, and then make a double bond break, you got a carbon and a carbon, make another double bond break, you have a carbon and a carbon, okay? So that's the way that that's going to be. The same thing with a carbon double bonded to an oxygen. A carbon double bonded to an oxygen, you're gonna keep the sigma bond, carbon-oxygen, you're keeping that, but then that carbon will have an oxygen. So it's like you have twice the number of oxygens, and then that oxygen will have a carbon. I don't think you need to even go that far, okay? Usually the point of attachment is right there to the chiral center. It becomes really easy to figure this out, okay? We'll go back to the pictures over here. We'll go back to the pictures over here. And if we're looking at the structure again, you're gonna see now that this carbon that is doubly bonded to the oxygen obviously will have a higher priority than a carbon that is doubly bonded to a carbon, right? I mean, I hope that we don't need to spend a lot of time with that. So this is gonna be priority number 1. This over here, priority number 2, this is 3, and this is 4, and again, you're connecting the dots, so this is gonna be your S isomer, yeah? Very good. We can do these till we turn purple, and unless you do them yourself, it's done for us, okay? So, yes,
Wait, why was I think I just completely spaced or something. Why was?
you were looking at me like in this moment of mesmerized. Really? What? Go ahead.
I totally missed, why is 2 the double bond? Why is that a higher priority?
Like this one, all right, so you keep this image, this is what I see. What I see is this, what I see is that this carbon here is a carbon that is bonded to an O, to an O, to an H, to a C. That's how I see that COH at the top. That's what I see. The C double bond C, this is what I'm seeing. This is a C that is bonded to a C, that is bonded to a C, to a C, to a hydrogen. Okay? This isopropyl is a carbon that is bonded to a hydrogen, to a C, to a C. And this back here, which is an ethyl, is a carbon that is bonded to a hydrogen, and to a C. That's really what you're seeing. I lose the whole class now. Everybody go, I mean, imagine if I was being observed by a dean today, right now. Do you think I would get high marks? This is like a disaster, right? I mean, this is looking pretty scary. So we're looking for points of attachments, right? This is my stereocenter, right? That's the stereocenter. And here, I have a carbon that is bonded to an O and to an O. While over here, I have a carbon that is bonded to a carbon and to a carbon. And here, so okay, do you see clearly that this is your first priority or?
Oh, yeah, yeah.
Okay, so this one we see clearly is first priority. When I look at this one that is becoming not so easy to see now, the double bond to a C with the isopropyl, that first carbon looks just like that carbon. You see that first carbon has a hydrogen, I have a hydrogen. You have a carbon, I have a carbon, and I have a carbon. So it's so far looking the same, right? So far it's looking the same, but when I get to these ends, all of these are hydrogens, while this guy has a carbon. So that's why that became your second priority. That carbon here has hydrogens on it, right? Okay, so this is a moment, again, right now, the isopropyl and this guy are looking the same. You're a carbon that is bonded to 1 and to 2, 1 and to 2 on the hydrogen. So that's why it is important that that carbon gets divided equally and that you show the other carbon. Because when I go to these guys at the end, all they have are hydrogens, while this guy has the carbon in addition to those hydrogens. So that double bond then is your second priority. The isopropyl became third, and this guy then is the last. Yeah? Everybody okay, or everybody sees it? Or? Okay. So if you have a double bond to a carbon, to put a moment of, in psychology called chunking, you know, let's take this information and see how I can just like grab it. Okay, if you have a triple bond is going to have higher priority than a double bond, because it's like you have, you know, so many more carbon-carbon bonds. If you have a double bond to a carbon and a double bond to an oxygen, obviously the double bond to the oxygen will have the highest priority, right? If you have a double bond to an oxygen and another oxygen, then again, you have even higher priority yet. So what you're looking for is that whole place where you find the first difference. I said to you that this chapter, what it was going to do was going to add another layer of nomenclature. So if you have a ring, so let's take a look at a ring. Oh my gosh. Fine papers. I complete so many papers, can you tell? Wow. All right, if we have a ring, and in the ring we have this, before, right, if we have that, and I come over here and I do all of this, can you assign R and S here?
No.
Somebody said yes or no. I hear yes and I hear no. Okay, so first of all, rule number 1, they have to show you the carbon with a stereochemistry consideration. Stereochemistry is wedges and dashes. If they just put a line, you don't know what that is. But when you're looking for priority number 1, priority number 2, number 3, and number 4, yeah, that's easy. Bromine is number 1 and hydrogen is number 4. But when I come over here, this guy hydrogen and hydrogen. When I come over here, this guy hydrogen and hydrogen. So you can't find a second priority. This is an achiral compound, not chiral. This is not chiral, 0. This has no chirality. In order for me to add chirality to this, I have to come up with another carbon, okay? And my other carbon now is going to look like this. I'm going to come over here. This is going to be my other carbon. And my other carbon is going to look now like that. All right? And so before, in first exam, we call this cis, 1-bromo, 3-chloro, cyclopentane. For this next exam, that will not give you all the points, because now we're going to say, name the compound using the new IUPAC rules and with absolute configuration. So you have to go ahead and determine if this is R or this is S. So let's take a look, okay? My carbon number 1, which is the bromine, will be all with red. Okay, yes? Chiral means that you have 4 different groups around you. So if you have 4 different groups around the carbon, that carbon is said to be asymmetric, have a stereo center, and be chiral.
How do we determine which carbon is chiral?
Right. So I'm going to say that this carbon is chiral, and I'm going to go ahead and draw the little asterisk. And I tell you why I'm going to say this, right? Bromine will be with red. All right, bromine will be with red. We already said that bromine was priority number 1. We had no problem with that. And we already said that hydrogen was priority number 4. right? So I'm gonna have them, I'm gonna write them kind of small, so we can see them as 1 and 4. We can go one away, so there's your hydrogen and a hydrogen, and there's a hydrogen and a hydrogen. So far, you would not know that that carbon is chiral, right? At this point, you do not know. But when we go further out, right, when you go further out, that carbon here now has a chlorine, while that carbon here has 2 hydrogens, yes? So this side has your second priority, right? So here, down here will be priority number 2, while up here will be priority number 3. Yes or no? Is everybody seeing it or no? Can I say something differently?
Is it just because chlorine has a lower one?
So you just basically go to the next best attachment, since those 2 carbons were the same, you went to the next one, seen the chlorine, you said that's the next.
Right, so you're looking for the first point of difference. Okay, you're going to, if you don't see it on carbon number 2, because carbon number 2s were equal, you keep going to carbon number 3, right? You got to the first attachments on 2, hydrogens, you cannot tell the difference. You keep going, and then you found that the chlorine here would have a higher priority. So that side became priority number 2. Okay, so that became priority number 2. So now, as you're doing this, as you're doing that, you can see that that carbon would then be R in its absolute configuration rotation. Is everybody able to see that? Okay, so you're going that way, that way. So carbon number 1 is the R rotation. Would you be able to do carbon number 3 without me? He will become blue. So it'll be a little blue sign. You have to do both. If you have 2 chiral centers, you have to do both. So does anybody know, what is this one going to be? Is everybody seeing S or? So chlorine is priority 1, your hydrogen will be priority 4, the exact same way, right? When I go to these 2 carbons, they're identical, they're 2 hydrogens and 2 hydrogens, so I can't tell them apart. I have to go to one further, the bromine will win, so this will be here priority 2, up there is 3, you're going that way, so now this is 3S. 1, 2, 3, S. So the new name now for this compound, forget your cis that we did in the first unit. Now this guy is going to be called 1R, 3S, and then you will add the 1-bromo, 3-chloro, cyclopentane. Okay, everybody okay? So 1-bromo, 3-chloro, cyclopentane, yes.
I don't see why the 3 is on that side and not 2.
You don't see why the 3 is on that side.
This, I mean, like, on the compound itself, when we're making, I don't
Okay.
feel like the 3 circles into the left side. Because it looks like the BR is going to be around this way. Unless I'm just seeing it wrong.
Okay, so perhaps, the drawing, all right, so let's just create, some basic rules, all right? So these are some basic rules. And basic rules is that you're gonna take this structure that I have drawn, and you're gonna try to do your inspection. And the first thing that you will do to inspect is if that 1 carbon has 4 different groups, right? So that's the number 1 thing that you will do. And when that carbon has 4 different groups around it, that carbon then will be allowed to be assigned absolute configuration. So, you can do that by manually assigning priorities to all of its attachments, like we did with the bromine, right? So, remember, the first thing that I did was use my rules of IUPAC, so the first thing that I did at the beginning was use my rules of IUPAC to name the compound. The rules of IUPAC were establish the parent, cyclopentane, look at the numbers, 1 and 3, 1 and 3, then go for the alphabet, so that 1-bromo, 3-chlorocyclopentane should not be a problem. Are we okay with that? That it was called 1-bromo, 3-chloro? We're good with that, okay. By drawing the wedges and the dashes, we're assigning where these bromos and chloros are coming to. So both bromos and chloros are coming towards you. Okay, then we call that a cis, and that's a different layer of nomenclature. A new layer of nomenclature is, hey, it is called cis because they're pointing in the same direction, but also because we can assign priorities here, right? And if we can assign priorities, and if we can assign absolute configuration, we like that nomenclature even better, okay? That nomenclature is the optimal nomenclature for chiral compounds. So, we looked at the bromine, and when we looked at the bromine, and the bromine was not the problem, I thought, that we knew that that was your first priority and the fourth, but when we're looking to find where we find the first difference, we didn't find it on carbon 2 relative to the bromine, right? These are carbon 2s relative to the bromine. We found the first difference on carbon 3 relative to the bromine. Because on carbon 3, and carbon 3 this way, that carbon had the 2 hydrogens, but this carbon had a hydrogen and a chlorine. That's what we call this side your second priority, and the one above the third, okay? And then we just connected the dots. When we connected the dots, that became the R. When I look at the chlorine, we're doing the same thing. So don't look beyond what you think you see in third place, you know, because I think you're trying to assume you're seeing this in a third dimension that perhaps might not be what's so good. I think that's what's going on. When we come over here and we look at the chlorine, we're doing the same thing. We're looking at the chlorine, because we're looking at the attachment of that carbon to a chlorine, to a carbon, to a carbon, to a hydrogen. So chlorine became number 1 and then the hydrogen 4. When I go again 1 carbon away to find a difference, I don't see it. I don't see it. So I have to go a carbon further. So I'm going to a carbon 3 to the chlorine, and carbon 3 to the chlorine, and this is when I see that that carbon, instead of having just 2 hydrogens, has a bromine and a hydrogen. So that became your second priority.
It's like that carbon 3 seems to be closer to the chlorine than the hydrogen on the other side, right? Is that what you were trying to?
I don't think I'm
I'll
seeing.
just ask you for opinion, because it's kind of complicated, like how, I know you can't really.
Don't make it so complicated, I'm serious. Try this time, try to just look at this literally. I mean, all you're looking for is finding differences and assigning priorities and then calling it a day. If you have, if you're seeing like the 3D out there, then you need to build the molecules. All right, we need to build the molecules to be able to see that. All right, is everybody having the same discussion that she's having?
I don't think, I don't know, it's my question, but.
I probably don't, and forgive me for
Oh, that's
that.
okay. No.
Forgive me, I don't think I'm seeing the question at all.
I can do that after lunch, if you want.
Okay, because I don't see it whatsoever.
It's okay.
Okay, I don't know. Right, I'll try to build them in a minute and see
No, I
what.
wasn't looking at the 3D or anything, I was just like trying to find, like, I guess it's because there's only like 1, 2 carbons instead of like 1, 2, 3, right? Like as you go around the ring?
Yeah,
Okay.
yeah. There are 3, yes. The distance between the bromine and the chlorine is, they're 3 apart, like like I'm on carbon number 1, so you are 2, 3 away from me. If I'm carbon number 1, then you are 2, 3 away from me. And if I'm carbon number 1, you are 2, 3 away from that one. Yes?
So could it be 3R1S or?
No, it cannot be that. And the reason why it cannot be that is because of the way that this is drawn, okay? So, and because they do have the naming priority.
Oh, so it's based off the name?
Right, so this time is based, if they were both the same, then yes, you perhaps would have been right. If they were both chlorines or both bromine, okay? Now, here's the story, okay? All of this to tell you, okay, all of this to say to you. If I ask you, what is the enantiomer? What is its enantiomer of this 1R3S? Because that's really what we want. What will be its enantiomer?
1S3R.
Is everybody there? So the enantiomer will be easy 1S3R. It's the total opposite, right? It's the total opposite, right? So I'm like, you said it was, yes?
So V1S3R, but the name would still be 1-bromo-3-chloro, right?
Right, so, but, so the name would continue to be the 1-bromo-3-chloro, whatever, right? So it all continues to be the same as that. Yeah? But what happened if I said, well, what is, I have 1R3S, what's then 1R3R? What is this?
A diastereomers.
Oops, sorry. Well, we don't know, right? We don't know. Is everybody there? So people that have read know, but if somebody said, we know that if the structure is 1R3S, its enantiomer is the opposite at every site. Its enantiomer is the opposite at every chiral site. So if I was 1R, you were 1S. If you were 3S, you would be 3R. But when you come here and you have the 1R and 3R, this is telling me that 1R is the same in both. Everybody? So the 1R is the same in both. That's identical. That's not an enantiomer. When you have this new stereoisomer, this is called a diastereomer. This is going to be called a diastereomer. A diastereomer in my book was like the catch-all category. Okay, the diastereomer would be the catch-all category. Can you see, would you be able to draw this with the same structure? Would you be able to draw this with the same structure? I think I have to do something before that. Hold on, yeah, hold on. Let's put this on hold just for a minute, okay? Let's try one more thing here. When I have this compound like this, I'm gonna keep the molecules all the same, all right? I'm gonna keep the molecules all the same so that life will be so easy. Okay, we see 3 different molecules. So far, the only thing we've really learned to do is maneuver the first. So for number one, I can see very easily that the rotation for number 1 will be R, right? Everybody can see that it will be R. Because iodine is the highest, so is bromine, so is that. So this is the only one that I can really do right away without having to worry about anything else. Okay? When you have the lowest on a straight line, you actually physically have to hold and spin. Everybody? When your lowest priority, it doesn't necessarily always have to be hydrogen. When your lowest priority is on a solid line, you have to hold and spin. It doesn't matter which one you hold, but the hydrogen has to be on the wedge, all right? So I'm gonna hold and spin. Can you do it before I do? I'm holding the bromine and spin. Bromine is going to stay here. Hold and spin. hydrogen is gonna come here. Who's on the wedge? Iodine is on the wedge, the chlorine is over here. Okay, is this R or S? This is S. Priority 1, priority 2, priority 3, you're going counterclockwise, this is S. On a test, when we ask what is the relationship between 1 and 3, you literally have to do this unless you see it in 3Ds, which by the way, not too many of us can do that, all right? So you have to find a tool. Yes,
So, I'm just gonna repeat what you said, so
Go ahead.
the one with the lowest priority, you're holding, when you're holding and spinning, you're holding the highest priority in place.
no, I can hold any one I want, okay?
But you chose bromine for this one.
I did,
Okay.
but bromine is not the highest priority. Can I repeat what you asked, that you said I said, and I'm
Yeah.
repeating it back? Okay, what I said was this. When your lowest priority is drawn on a solid line, you must physically rotate and move the lowest priority to the back. Who you hold is really not important, okay? By having been doing this for too long, I usually hold one of the ones that are on the solid line. And what I mean by this is like so. If this is my molecule, take a look. This is exactly what we had there. Did you see that? Well, more or less. So, the white ball is usually hydrogen, and the hydrogen is in the solid line. Do you see that they're in the solid line? Everybody is with me. So all I did is I held on to one and I just spin to put that hydrogen in the back so that then I could just assign the priorities. Back again with that one, I did not have to hold this one. I could have hold this one and then rotate. Did you see that? It just makes it harder to see the spin. It's much easier to see the spin with a solid because this is the chirality of it. So that's the only reason why I picked the solid line. It's much easier for me to explain it, okay? But by convention, go ahead. Yes.
So it doesn't matter which one you grab onto, but you just have to make sure the hydrogen gets into the back,
The lowest,
the lowest.
the lowest priority, the lowest priority. This time is the hydrogen. But it doesn't have to be a hydrogen, you know, it could be a methyl, it could be an ethyl, it could be an isopropyl. The lowest priority is in the back, okay? But listen to this, right? So, by convention, back again. So let's take a look at the priorities here. So, my chlorine is priority number 1. This is another example. I'm just finding color balls that will be easier to explain, right? Chlorine is number 1, oxygen is number 2, nitrogen is number 3. What is the rotation here? Chlorine 1, oxygen 2, nitrogen 3. We're rotating R, right? We're rotating R. What is the rotation now? Chlorine is 1, oxygen is 2, nitrogen is 3. What is the rotation now? S. Everybody, S. So by convention, your hydrogen is always in the back, and that's how you assign. So when you have this one, and your hydrogen is in the front, which is the lowest, you can assign and switch. Everybody? You can assign and switch. So when I'm looking at this one, and this is priority 1, priority 2, priority 3, and I'm going like clockwise, right? Priority 1, 2, and 3, and I'm going clockwise, and I say it's R. Oh no, but it's S, because the lowest is now out of convention and to the front. A moment of chunking. Here we go. Let's see if everybody hears the same thing. Go ahead.
That only works when the lowest is in the front though, right?
That is
Not on
right.
the opposite side.
Very true. So here we go. When you have a carbon that has 4 different groups and is drawn in a stereochemical, it's drawn in an sp3 type thing. If you have solid lines, let it go, move on to another question, okay? But when we draw wedges and dashes, that carbon that has 4 different groups, it's a chiral carbon, okay? By convention, Canning-Gold-Prelog, with their rules, okay, to assign absolute configuration, you always want to hold the lowest priority in the back, and you do the rotation, okay? And I'm seeing it like that. But you from over there are seeing it very differently, okay? So by convention, hold, go to the rotation. If the lowest is on a solid line, you must physically rotate and then assign. If it's on a solid line, the lowest on a solid line, you physically hold, rotate, and assign. But if the lowest is on the wedge, you assign and switch, okay? If the lowest is on the wedge, you assign and switch. This is why. Go ahead.
If it's not a chiral center and it's drawn like that, we still can't do absolute configuration, right?
Right. That's how we started with that bromine on carbon 1, right?
We just did this for a sense of consistency, right? Because if you have everything facing the same way, then you can name it consistently instead of having that mix up, because depending on how you do it, you still have to start. Just to be consistent.
Okay. I don't know if you want to say that out loud, you know, usually
I'm just,
they.
like, talking to you,
I know,
really.
I know. So, okay, so, you know, I've been here at Solano College for many years. We're gonna try to bring some breathing moments here. So, many years ago, I was teaching in the Vallejo Center. I was teaching Chem 10 in that little amphitheater. I don't know if you remember the amphitheater. Have you been to the Vallejo Center? Okay. Well, the Vallejo Center has a big room, which is kind of like a little 308, which is like an amphitheater. And all my students would sit in the very front. I was teaching Chem 10 and they would sit at the very front. Well, the dean came to evaluate me and she sat at the very, very back of the room. You know, I mean, we can sit like 200 people in this place. And I had everybody like how you guys are, really close to me. And this person is way at the top, the very bottom, very top of the room. Very good, the dean. And then somebody asked me something like her, and I went to the board and I started to explain. Well, that was the one negative that she wrote, that I didn't repeat the question so that everybody could hear it, because I started to explain something that not everybody heard. So, but we've decided that this is between you and I, because I don't think I can repeat it, okay? All right. What I'm trying to do is create one more tool, right? One more tool, one more tool. In the event that we go ahead and do something like this, for you to name the compound, right? So let's say we ask you to name the compound. And here we go again. So name the compound. And we already know that you're naming the compound using all you know, right? So you're naming the compound using the IUPAC and the absolute configuration. So name the compound using IUPAC and absolute configuration. Absolute configuration, everybody knows already, this is your R and your S. Okay, and I draw your compound. Like that. You have to name it. So let's start with what we know, right? It's usually a great idea to start with what you know. And regardless of R and S, what would be the name of this compound? So forget about that. What would be the name of your compound, regardless of what you know? Is everybody okay, right? So 1-bromo-4-fluorocyclohexane, so this is the story of like laying bricks on this wall. So the 1-bromo-4-fluorocyclohexane we already got, right? That name we already have. Now the next layer is the absolute configuration, right? And that one is when you have to try to find priorities and all of that, right? So let's again make bromo be red. So let's again make bromo be red. And so bromo being red here, that is priority 1 and the hydrogen is 4. And I already am going to assign and switch, right? Everybody? Bromo is 1, hydrogen is 4, and whatever I get, I'm going to assign and switch because the lowest is to the wedge. All right? So it's like you're now not assigning it like that, you're assigning it like that. Right? So who's going to be priority number 2? The same, everybody? Can you? No. Is everybody there? So I go to the second, no, the same. I go to the third, the same. Who's going to divide the fluoro? So this is the beginning of what is called a pseudo-chiral. It looks like it is, but really it isn't. Is everybody there? Because you could not find the second difference. Everybody, the same here, the same there, the same here, but this one we cannot divide. This compound is achiral. This is not chiral. This is an achiral compound because you cannot find that point of attachment. So if anybody asks you to name that, that will remain the same story as 1-bromo-4-fluorocyclohexane. Now take a look at this compound now again. We come over here, we try to do the exact same thing. I put the bromo, I do the wedge and it's a hydrogen. I come over here, I do the hydrogen and I do the wedge that is a fluoro. Now tell me what you can do now. What happened with carbon number 1?
Or S.
Okay, so priority 1. Okay, priority 1. How many people say R? How many people say S?
S.
R's. S?
S.
Okay. R, S, R, S, R,
Flip it.
S. All right. So let's see. I can't think anymore. I'm like the brain that.
You switch it to
All right.
this.
So I
This
know 1
one.
and 4.
There's R, and then you switch
Oh,
it
wait a
as the wedge.
minute.
The lowest of the wedge.
Clockwise is all right. So this one is.
Who's that? All right, let's try. No, it's not the same. All
No,
right,
no,
so
I'm
let's
saying,
see.
no.
All right. So priority 1, priority 2, 4. Sorry, 1 and 4, 1 and 4, 1 and 4. Okay, I'll go to the second carbon. It looks the same. I can't find a difference. I'll go to the third carbon and I find a difference. You've got 2 hydrogens and you only have 1. So this here would be priority 2. So this carbon is 2. Up at the top is 3. You're going this way, everybody. You're going this way. So you're going R, right? You're connecting the dots like so. Okay? So I'm going R, but the the lowest is on the wedge, so I switch. If your lowest is on the wedge, you assign and
Can you go for the
switch.
second one?
So one is S.
I got S.
3S?
You assign and switch. If the lowest is on the
One is
wedge,
3S.
you assign and switch. I'll take a look at number three. At number
One,
three,
Roma,
we have
2, 4,
priority
7.
number one. Let's make fluoro be pink. So this is one and this is four, and we do the exact same thing. I go to carbon number two and it's all the same. Carbon number two is all the same. I go to carbon number three, and I see that the bromo has a higher priority, so this is two and this is three. So I'm going 1, 2, 3, which is that way. So it is S, right? And it stays. It's S and it stays. And the reason why it stays is because the lowest is on the dash, okay? So you need the lowest on the dash. Now here's the story, right? So that's the name for that compound. And yes, you will write the rest of it, the 1 bromo, the 3 fluoro, cyclohexane, right? That will be the entire name for that compound. The 1S, 3S, 1 bromo, 3 fluoro, cyclohexane. The enantiomer, if I ask for the enantiomer of that compound is going to be then what? 1R, 3R. That will be the enantiomer. Opposite at each site, right? Opposite at each site. If we ask for the diastereomer, what can somebody say? You can say 1S, 3R. Can everybody see? You keep one the same, you switch the other. Or somebody said, well, I didn't want to do that. I switched the first and did the other. Right? I switched the first and did the other. Is there any other one? Are there any other diastereomers? I don't think so, right? We're keeping one the same and then the other. All right, we're moving on to somebody more fun. This gentleman named Fisher. Fisher said, oh my God, I absolutely hate this. Fisher said, no way. You know how she said she cannot draw? Fisher says, I cannot draw either. Fisher said, take your molecule and try to flatten it out, right? So he says, try to flatten it out. You see what's happening? Who's onto the table? Like trying to get down into the table. Colors. Okay. I'm trying to push you into the table. Who's going into the table? Blue and red, right? Blue and red are going into the table. Who's kind of sticking out of the table? White and green, right? All right, so that's what he's trying to do. His name is Fisher. Supposedly, he's going to simplify our lives, but I can already see no. Okay, these are going to be called Fisher projections. And in this Fisher projection, he's taking that carbon, and that carbon he's saying, oh, there are going to be 2 that are going to go into the table, and there are going to be 2 that are going to stick out of the table, right? Like that. Oh, I'm trying to draw this better. So this is how he sees that chiral carbon. He sees that I'm going to have it like that, right? Can you see that, the 2? I mean, you really need to see this, otherwise we're in like deep doo-doo-doo-doos. All right, we need to see that 2 are coming out. Can you see that if I draw it like that? Perhaps everybody's eyeballs back on the screen. You can see that these 2 are coming out, and those 2 are going down. I think this is a better way perhaps to see it. Okay, these 2 are coming up to the front, these 2 are going behind. So he also said, oh wow, I'm not gonna be drawing this, so we're gonna draw it like this. And your horizontal lines are the wedges. So these guys are the wedges, the vertical line is going to the back. The vertical line is going to the back. Remember that to the back, by convention, this is how you assign your whole absolute configuration. So if I put a hydrogen here, I put a bromo there, I put a OH here, and I put a fluoro here, would you be able to assign R or S on this one? Yes or no? Bromine is 35, fluorine is 9, O is 8. So this is priority 1, this is priority 2, this is priority 3. Is this R or S? Is everybody seeing R? Very easy, this is R. You are going to the back, you have the lowest on the back, right? So you have the lowest in the back. So you can go ahead and assign and save it, because the lowest is in the back, that is R back. Okay, you're gonna name this compound. If we're naming that compound, what would that name be of the whole compound?
Two bromopentane.
I heard 2-bromopentane somewhere. That is correct. That is correct, not all the points. You said S, she's saying S. Does everybody agree? Yeah? All right, let's see. Priority 1, priority 2, priority 3. You're going this way. You're going this way, so you're going this way, which is R. But the lowest is on the wedge. You assign and switch. Okay? So if your lowest is on the horizontal line, you have to assign and switch. So S is correct. And this compound then is going to be called S2-bromopentane. Okay, that will be the name for this compound, S2-bromopentane. Okay, ready for one more? You have the option to finish discussion 7, 8, I have no idea how many. Do you have anybody has the discussions really close by? Yeah. If you don't, oh good. All right, so this is what I'm expecting everybody to get done by Monday. Yes, I see you guys again on Monday? All right, so I see you again on Monday. See this, discussion 6? There's no reason why you cannot get discussion 6 done. There's no reason why you cannot get discussion 7 done. So homework is 6 and 7. Homework is 6 and 7. Let me go ahead and do this on the left-hand side. Okay, so 6 and 7. Discussion 6 and 7 due. We have a dry lab on Monday. 6 and 7 due Monday. Let's try to do one that has more than one chiral carbon. Okay, so I'm gonna.
Are we gonna have mastering chemistry?
I wanna say yes. I'm not sure. I'll have to look again. You know, when I set this whole mastering, I do it at the beginning of the semester, and I haven't had time to look. So I will send an email. Assume yes, unless I send an email saying no. Okay, so the assumption is yes unless I say no. Oh, thank you, yes. Alrighty, what are we gonna do here? Priorities. carbon to chiral? Is this carbon chiral? I guess that's the first question that we have to determine. Well, it has 1, 2, 3, and this mess that I don't know. It looks like I have 4 different groups around it. So I'm gonna give this guy a little asterisk. And the very bottom one, I'm gonna say that you have 1, 2, 3, and this mess at the top. So also that one is chiral at the top. Right? And so now we have to go ahead and assign priorities. Direct attachment. I'm directly bonded to an O, to a C, and to a C. That's a C right there. So the OH is priority number 1. What's between these 2 carbon? Who will be the second priority? The CHO is this, right? That CHO is this. This is a carbon that is bonded to a hydrogen and now to an O, right? But that's a double bond O, so it's like you're also bonded to an O and you're bonded to a carbon. That's what that looks like. So that carbon here is like it's bonded to 2 O's, and this carbon here is only bonded to 1 O. Yes? So the aldehyde is the second priority. This mess down below should be third. The hydrogen is fourth. Right? Yeah?
You lost it when you named that one, second, you named the CHO, second priority.
Right. The CHO, you know, is like, it's an aldehyde, so the CHO is really this. The CHO is this. That's the CHO, it's an aldehyde. And an aldehyde in the assigning priorities is like you have this carbon that was originally bonded to a hydrogen and to an O, but a double bond to an O is explained as I really am bonded to 2 O's, and that O is really also bonded to 2 carbons. Just look that you have 2 O's on that carbon. So that carbon has 2 O, well, this carbon only has 1 O, the CH3, so that is your second priority. So you have 1, 2, 3, you're going that way, which is S, but because you're on the horizontal line, that guy is R. So this guy will be the R group here, or the R rotation. What happens with the bottom? The bottom should be easier to go ahead and figure it out. The bottom is easier to figure out. Which one is priority 1? The OH is priority 1. Where is priority 2? At the top, right? The top is priority 2. The methyl is 3. The hydrogen is 4. You're going 1, 2, 3, which is S, but really it's R. So this one should also be R. So your rotations here are R, R. Okay, that's the way that it's gonna have to be done, right? The way that you see it.
How would you name that?
Oh, Chem 4. You will name this in Chem 4. So for you, 1, 2, 3, 4. This will be 2,3-dihydroxybutanol will be the name for this guy. Chem 4, Chem 4. Right now, all we want to do is to be able to see that there's chirality and rotation. It's been great seeing you. I have to say, not my best lecture. I'm